All right, so just to continue from last week, just to be clear on the gelation. So hopefully you already understand the meaning of denaturation, the difference between native protein and denatured protein, and we use heat as a way to denature protein. So after the protein has been denatured, then the protein molecules aggregate, they come close together, and by coming together, they can form all kind of bonds between them. By forming this bond, mostly non-covalent, they cause the entrapment of water. So the water got entrapped. The water cannot go anywhere, and it become gel. The gel become a continuous network. And gelation is defined as the balancing between protein-protein interactions and protein-solvent interactions. Okay, we cannot do this in class, but your senior, what we did when we were in class is we bring some rubber band into the class, and then we join the rubber bands together. Each rubber band is like amino acid. So imagine you have a long chain of amino acids. We call this protein. So we start the process with a protein that is not yet denatured. It is native proteins. And then we apply, after applying heat, of course, we don't really apply heat, just to show you that the rubber band, the strings of rubber band now become denatured protein. So they can combine, they can aggregate, and then they can form bonding between other rubber bands. And between those rubber bands, we managed to entrap water molecules, the balloons. So you can imagine if there are like millions and millions of rubber bands, there are millions and millions of the balloons, it becomes a gel. Okay, so that's how the protein is used in the food system to become gel, and gel contribute to texture. Texture is good for eating pleasure. Okay. Emulsification, just recap, what you need to know here is that oil and water will not mix. If we agitate it for a long time, we leave it on the bench, it will go back to the original because oil and water will not mix. And then we introduce protein. Actually, any other emulsifier can do. Yeah. So that is the protein, noted as that. That is the protein. And this area here is the interface. When we say interface, it means the interface, the phase between the oil and the water. So the protein, it has this hydrophilic, hydrophobic, so it has the tendency to go to the interface because the hydrophilics will want to be associated with water, and the hydrophobic will want to associate with oil. And then we agitate them, and you will see now we have an emulsion. It become emulsified oil droplets or emulsion. Now, after you leave it for a long time, the gravity can no longer separate oil and water. It become stable emulsion. Now you can distribute whatever you want to distribute, maybe the flavor, maybe anything, the oil droplets. Okay, done with that. Okay, to form a good emulsion, the protein has to be able to rapidly adsorb to the interface here and form a stable film around the oil droplets like that, and rapidly and readily open up and orient hydrophobic groups towards the oil phase and hydrophilic groups to the water phase. So that's a normal criteria or characteristic of a good emulsion. This is I got it from the internet. Angel food cake. You have egg yolks. I think they use it as a lecithin. Lecithin is a good emulsifier. And then they use 5 egg whites. So you know now, egg white has a lot of protein. And that protein can function as a foaming agent, as gelation agent. Okay, so you beat the eggs, and then the eggs will start to form foams. Yeah. So foaming is also a functional property. It's like gelation. Foams are similar to emulsion, where air is the hydrophobic phase. So you just reverse. Instead of foaming, you just say instead of emulsion, now you talk about foaming. Yeah, similar. The concept is very similar. So you have protein here, which is natured, and then you perform agitation. You do some kind of very strong whipping, mechanical agitation, and then it becomes denatured. It's like heating. Because of more and more agitation, that protein, the denatured protein, will go to the air. Same process like before. Now it is adsorbed or form films, followed by the entrapment of air. When gelation, we talk about gelation, we are talking about entrapments of water. With foaming, we talk about entrapment of air. Okay, so air on top, of course, water at the bottom. So you do agitation in the presence of protein there. So after certain agitation, the protein will surround the air, and when the product is cooked, the protein is cooked, and the air cells stay. So you have cake with foam, and that's how they form. That's how the protein performs its function as foaming agent. Combined with gelation, it cook, so it retain the air inside the cake. Okay, so we have done this selected properties, functional properties of protein: solubility, water holding ability, gelation, emulsification, and foaming. Okay, done that. Okay, can you guess what is this? What on earth is that? You got it right. I will send you money. I'm serious. Going once, going twice. Nobody has answered. Okay, nobody has answered, so I can send money now. All right, what you do? Coconut milk? No. That's very logical answer, eh? Okay, what you do, guys? You see, when you see your mom want to make a chicken soup. So she will like heat the chicken or boil the chicken for 2 or 3 hours. You know, the chicken will boil the fat. The fat from the chicken will be extracted out, it becoming to produce this chicken soup. And you do not want this chicken fat, so you leave the soup cool overnight. Leave it there overnight. Because the temperature is cold and all that, you will see the fat of the chicken coming out from the soup like that. So you can separate, you can remove it from the soup. So it's chicken fat, okay? All right, so what I want you to do, I want you to take a piece of paper and put it on your forehead, that's it, and write the word E. Take a piece of paper, put it on your forehead, and write the word E on that piece of paper on your forehead. Okay, done? All right, depends on your empathy. Some people will write E like this guy on the left, some guy will do it correctly, will get E on the right. On the right is supposed to be this E, yeah. So it is about empathy. If you want others to understand you write E like that. Somehow, some people they are thinking for themselves. They got it all wrong. So you know who you are. Are you thinking about yourself, or you are thinking about other people who want to see you? Okay, so why I'm doing this? This is E represent fat. Fat is so now you cannot forget about fat. Fat is the structure is like that. It's like E. Yeah. You see here, it looks like E. Oops. All right, so we have glycerol, and then we have fatty acid, fatty acid, fatty acids. So 3 fatty acids combined with glycerol, we have fats, or we call it triglycerides. So you cannot forget the E in fat. Yeah. Okay. Oh man. So you will always remember this E as fat. You cannot forget that because of the mistake you make. So this is just basic notes. Don't worry. Lipids are basically non-polar, relatively non-polar, right? Well, mostly non-polar. Just give you very basic info. Fats and oils are chemically known as triacyl glycerols or triglycerides. Let's call it TGs. Yeah, TGs are triesters of glycerol and fatty acids. Done that. So we have glycerol, simple organic molecule, 3 carbon molecule containing 3 alcohol groups. And then we have fatty acids. There are many types of fatty acids. Organic molecules containing chains of carbon bound to hydrogen plus COOH acid at one end and a methyl group CH3 at the other. Okay, and what makes a fat special? This ester bonds. Yeah, ester bond hold fatty acid to glycerol, joining the OH group of glycerol to COOH group of fatty acids with the loss of water. Okay, so we're talking about all this. This is the OH group, this is COOH groups of fatty acids. So we join them together in a bond called ester bonds here, the green bond. So we form ourselves, now we form ourselves TGs. Before it's just glycerol with fatty acids, now we have TGs. So polypeptide or peptide bonds is protein. Now we talk about ester bond, which is fats. Okay, so you have to note the ester bond. You will remember the E. Okay. Okay, I went to Thailand some time ago. Just to remind you, some women in Thailand still having that ester bonds, but we have no ester bonds. Our neck is so short, we are not qualified to put on that metals ester bond. You're laughing, aren't you? So saturated and unsaturated fats. When we talk about fat, we cannot avoid this term, saturated versus unsaturated. So separate them. So you know, fats and oil, they have mixtures of fatty acids. Some fatty acids are saturated, some are unsaturated with all kind of length and degree of unsaturation. And let's be clear, saturated is the one with does not contain any carbon-to-carbon double bond, therefore more stable. Unsaturated fatty acids contain carbon-to-carbon double bond, therefore less stable. Can be monounsaturated, having one double bond, or polyunsaturated fatty acid, or sometimes we call PUFA, PUFA, having 2 or more double bonds in the chain. Okay, and you see here example, saturated fatty acid mostly in the solid kind of fat, unsaturated basically in liquid, and you see the banding there. Because of the double bond, the fatty acid actually some kind of bending, and that contribute a lot to the physical properties of the fatty acid. Yeah. Okay, we have this example of fatty acids characterized according to saturation. You see here, C40, that means it is saturated, no double bond. Until we have C18-1, monounsaturated, until we have C25, 5 double bonds. Yeah, I'm not sure what is behenic saturated, or C22, 0 double bond. Okay, just example. Okay, then we have for you to differentiate between cis and trans fatty acids, or trans fat. And this is only for unsaturated fatty acids. When we talk about cis versus trans, we don't care about saturated. We just talk about unsaturated fatty acids. So unsaturated can come in 2 configurations defined by their structure at the double bond. Okay, it is very difficult for you to imagine. You have to look at the structure. Okay? So cis here, the hydrogen atom bonding to the C double bond located on the same side, versus trans, hydrogen atoms attached to the carbon atoms of the double bond opposite each other. Okay, you can only appreciate if you see the picture here that I just snapped from the books. Okay, the trans form is the no bending one. No bending. So you see the hydrogen attached to the carbon atoms are on the either side of the double bond. This is a double bond. That is double bond. So that's hydrogen. That is hydrogen on the other side. Yeah. Compared to the cis form, which is this is the hydrogen bond, and that this is a double bond. This is the hydrogen that is attached to the carbon on the same side of the double bond. Okay, so that what makes the cis, the trans and the cis are different is in the nature of bending. Yeah, and it says here it's good to bend. But why it is good to bend? Okay, I wrote down here to make it clear using my pencil. So carbon, hydrogen here and hydrogen there, same like here. That means it is trans, and hydrogen go there and hydrogen there, same side. It is cis. Okay, so there are many reasons why this is important. We'll discover later. Okay, here it is. It will affect the physical properties of the fatty acids and the fats, of course. Example here, the saturated stearic acid C18-0, 70 degrees C, the melting point. Oleic and elydic, same carbon atom, C18-1, unsaturated. And oleic is cis, while elydic is trans. Look at the melting point. Oleic is 19, elydic is 43. So, if you are in industry, you prefer elydic because the melting point is higher. The trans configuration results in higher melting point than cis. So, elydic is solid, oleic is liquid because the melting point is lower. Yeah. Okay. Industry love trans. Why? Okay, we just go here first. Melting point definition, temperature at which the solid is converted to liquid. You know this. So fat molecule we know in crystal form, and the strength of the bonding forces between the fatty acids in fat crystals determine the melting point. So fatty acid exhibit unique melting points. Triglyceride with array of 3 fatty acids exhibit melting point based on which fatty acids are present. The types of fatty acids determine whether TGs will be solid, liquid, or even plastic. You can spread like butter, like soft spread. Okay, melting point is determined by many factors such as fatty acid length and, of course, degree of unsaturation. If everything is equal, short chain fatty acids show lower melting point than the long chain. Saturated have higher melting points than unsaturated. Okay, so saturated always stay at a like a solid. Unsaturated tend to melt faster. When a mixed fat is heated, the steric, oleic, palmitics. This is 3 different kind of fatty acids that form a fat. The melting is often gradual and over a range of temperature rather than one distinct measurable value. So you can imagine it's coming down like this. It's coming down a range of temperature. Yeah, it's not zoom. It's not going down rapidly. It's going to be a range because of that mix of fat, reflecting impure fatty acid composition. So cis configuration has lower melting point than trans. We have seen this. And this is just to illustrate the difference between the effect of cis versus trans. Even though they are basically similar, look, similar, C18-1, but because of the location of the hydrogen there and on the double bonds, it changed the physical properties tremendously. In this case, it changed the melting point, from 43 to 19, from 19 to 43. All right, so we've done that. You should be able to answer what are the implications of cis and trans configurations on melting point of fats. So that was the answer. Okay. You have eaten nasi minyak, yes? To Stephen, nasi minyak is basically oily rice made with a lot of oil. And so which one has better flavor? Nasi minyak or ordinary rice? Answer. Of course, nasi minyak. See, nasi minyak. So also learn sometime later on. Nasi minyak also make you become full faster. You become the satiety is reached faster. You become satisfied faster, and that is the strategy of Malay wedding. In the Malay wedding, they will serve you nasi minyak so that you eat less. Okay, that is about just to illustrate to you this point that fat property, it carries flavor. It carries flavor compounds. Fat molecules themselves actually contribute to flavor. All right, so we talk about fat. So this is butter. B there, here, this B. The B in the middle is actually butter. The A, the C, the D, several fractions. Just to show you the impact of solid fat on the temperatures of melting. So you see that the solid fat becoming less, meaning it is melting. Yeah. So this is a function of the percent solid fat content. Comparison between melting behavior and solid fat content. So when the solid fat percentage is high, like A, when the solid fat is high, the product melts at higher temperature, like A. Then when the solid percentage in the sample is low. So melting behavior affects the ease of spreading. So you want to make butter, you want to consider that the solid fat content has to be right, not too much, like A, it doesn't spread very well. Not too little, like D, it doesn't spread at all. It's almost like a liquid. So B or C, it looks like a more or less good butter. Next, we talk about polar lipids. I want you to be surprised, but you are not surprised. Polar lipids. Polar lipids. I thought lipids are non-polar, but there are polar lipids. These lipids have polar groups, potentially charged hydrophilic groups containing oxygen or nitrogen in their structure, and thus have a degree of water solubility. Okay, so accept this fact that lipids can be polar, therefore they have a degree of water solubility. Fat can be soluble in water, but not all fat, of course, only these polar lipids. A good example is lecithin or phosphatidylcholine. In food, lecithin can function as emulsifier. If you eat eggs this morning, the egg yolk has plenty of lecithin. It's a good emulsifier. Okay, again, you cannot understand if you don't see the structure. This is a good structure. Glycerol, again, becoming the connecting structure. This is the glycerol. It has two fatty acids. Okay, so this fatty acid will be the hydrophobic parts of it, and we have the choline side, the phosphate side here. This is the hydrophilics, the charge, the polar side. So you can expect this kind of, it can interact with water. So hydrophilics will be bound to water sites. Hydrophobic will be away from the water, and because of that, we learn in lecture on water, you can make this particular polar lipid soluble. Well, some degree of solubility. And a better structure is this one, the hydrophilic head versus hydrophobic tail. So we have 1, 2 fatty acids down there, and you have the phosphate and glycerol side. Okay, you can spend your time to have a look at this guide. This is a very good compound interest. You can Google this. You can see their Facebook. They summarize a lot about chemistry. So in this case, they summarize about triglyceride and fatty acids. So from there you can get what is saturated, what is monounsaturated, what is polyunsaturated, and trans. It gives you a quick like a note. All right, so it's 10:29. We still have time. So we have done the basics properties of fats. These are going to be very useful when you learn deeper on food chemistry. For this course, some of it may come in the test. Yes, you're going to have tests somewhere in the beginning of next year, long time to go. Early January is supposed to be exam time, but we don't have exam. But I will give you one test, online test, yeah. We'll cover everything, so don't worry. Okay, we're going to go into selected reactions of lipids. In industry, they do this fractionation, hydrogenation, hydrolysis, esterification. And what they do not want to have oxidation. These are reactions of lipids. Okay. The famous one is hydrogenation. It's addition of hydrogen atoms to the unsaturated bonds in unsaturated fats. See, industry, you are going to join the industry. What you do, you force the addition of hydrogen atoms to the unsaturated bonds in unsaturated fat, i.e. you change from the liquid cis fat into solid trans fat. See, a lot of cis there, cis, 4 cis. Now only 1 cis remaining, the rest become trans. So you change from liquid to solid, meaning you raise the fat's melting point by hydrogenation. This makes the liquid harden into semi-solid fats. Fatty acid with most double bonds hydrogenate more quickly than the less saturated ones, so it is also more stable. You industry love this. You want your fat to be stable. When you fry it, use it for frying, you want it to be more stable, so people will buy your products. That's why you do hydrogenation. So the process can be controlled. Vegetable oil into butter, for instance, there are processes for that. You can make butter from vegetable oil while retaining the high linoleic and oleic acids. But the problem with the hydrogenation, the percentage of cis is changed to trans. We know this. And in trans form, linoleic acid, which is dietary essential fatty acid, our body wants this linoleic acid. It becomes biologically inactive. So, A, why? B, so what? I think by now you should be aware that people are no longer crazy about trans fat. If sometimes you see products on the state no trans fat, meaning that they do not do this kind of hydrogenation. So now, if you want to buy peanut butter or some kind of oil products, that's the kind of information you should carry with you. Does it has this trans fat? How much trans fat? You want it to be 0. Okay. Since unsaturation is reduced, the tendency of fat to oxidize is also reduced, making the hydrogenated frying oil more stable, longer frying life, and higher smoke points. So industry love this, but when it comes to your body, well, the essential fatty acid is no longer available. Why? Because we are not used to the trans fat. We don't know what to do with trans fat. We are so used to cis form. Okay, it's not so good for health. Okay, number 2 is fractionation. Basically, it is a separation process. Oil is separated into fraction with each specific properties. So you have degree of saturation. The more saturated, the higher the melting point. So you can play with these fractions. So it is possible to split oil into higher melting point component and lower melting point components. So you will allow crystal portion to be separated from the liquid portions. And then this portion can be further fractionated. You are Malaysian, most of you. So this fractionation is important for palm oil. Okay, we're going to use palm oil as an example. It's a mixture of different fatty acid with specific melting point. The melting point of palm oil is about 38 degrees Celsius. So palm oil can be fractionated to produce a lot of variety of fraction that can be applied in a variety of products. That's the beauty of it, yeah. So you can start here, melting point 38. You have SAFA, SAFA, MUFA, PUFA. MUFA we know, mono unsaturated. PUFA is polyunsaturated. SAFA is saturated lah. Okay. So by using fractionation, we can play with it. You see the 51%, 38%, 10%. You can form olein, you can form stearine. Olein, it means 46% is SAFA, 43% MUFA, 11% PUFA. Stearine means 67% SAFA. Ooh, very high SAFA. It goes up from 51 SAFA to 67 SAFA. And you reduce MUFA and you reduce PUFA. So you can imagine it is in terms of solidity, in terms of melting point, it is changing. And then you do more fractionation. You see from olein, you do more fractionation to super olein, melting point 5 degrees C, or you can produce mid fraction, melting point 28 degrees C. Same thing with stearine. You can fraction further to melting point 48 degrees C, soft stearine, and super stearine, melting point 60 degrees C, which is much higher. So what do you want? You want it to be high melting point or you want it to be low melting point? Because different products will ask for different melting point properties. So we have different fraction now. Super olein is the least saturated here, super olein, least saturated, to super stearine, melting point 60 degrees C, more saturated. Okay, it's like playing with your palm oil by fractionation. Of course, the process is very complicated. You're going to learn in one very specific course on palm oil. So the application is, for instance, super olein. You can recall super olein is here, 5 degrees C melting point. And then mid fraction, the super olein can be alternative for liquid oil or making chocolate spread, for instance. For mid fraction, recall mid fraction is here, melting point 28 degrees C. It can become filling fat or cream fat. You can put on bread. And stearine, this is kind of hot oil. Stearine, super stearine. Soft stearine can become bakery and softening. Stearine and super stearine, a lot of SAFA there, 88%. They can become substitute hydrogenated vegetable oils and fats in margarine. Okay, so margarine, you know lah, how hot it is. So mixing, now you can mix of different fractions or with other oils, make it possible to produce product with specific melting point necessary for certain application. Okay, so that's what it's all about. Okay, I hope you get it. There is a video in YouTube. I explain all this again and again. Okay, number 3, esterification. The word ester there, I put that in red just to remind you what is ester. It's the bond. So we can play around with the esterification. Yeah, removal of fatty acid from glycerol by using metal salts or enzyme lipase, and their subsequent rearrangement. You see the color there? Rearrangement or recombination into numerous configurations. Because of this rearrangement and recombination, you will have different properties already. Reform fatty acids. Beginning the green was in the middle. Now after rearrangement, the green will go up. So it is possible to modify fatty acid distribution within 1 Tg. And because of that, you yield a Tg with desired properties like you want hot fat is esterified to produce mixed glyceride with improved creaming. Okay, again, recall Ester Bond attached to Fa to glycerol, therefore the term esterification. It is these bonds that are broken and then reform during the reactions. All of these technologies are established. They use all kind of metal salts and all kind of enzyme. Yeah. Coarse, crystal, grainy, textured fat like lard can be changed to lower melting point, finer crystal size, more plastic, smoother texture, and mouthfeel. Okay, simply by broken and reform. It is even possible to produce TG with lower calories, yeah, because you have this shorter fatty acids, maybe from other TGs. So we have like the bottom there. This particular yellow one is the shorter chain, therefore lower calorie, and we transfer that to that fatty acid there. This one is high in calorie, so now it become lower in calorie. It is possible. The technologies are there. They're not going to reveal everything. Industry will keep the secret to themselves. Yeah. Okay. It's 10:42. I don't want to go further. Hopefully you get the point today. What fat all about? Yeah, it is very important component, especially for food processing and manufacturing. So next week is the last lecture on food components, and I'm going to go into basic nutrition a little bit, and after that Dr. Chang will take over and she will do mostly on ethics. Yeah, you have to be given exposure on ethics. Okay, any question from you? Stop recording.